Welcome all to the second lecture of Principles of Statistics. So in the first lecture, we spoke, well, first of all, we introduced a few concepts. I was recalling some concepts from probability, and I sort of introduced the course, and in a very high level way, we were talking about everything that we'll be covering. And then we started with the so-called likelihood principle, which is probably the most important principles for statistics. So today we're going to continue with the likelihood, which I didn't really define in general, and then we'll look into some aspects of it to start gaining intuition as to what the maximum likelihood estimator does, or how it should be behaving, and whether it does or not, from a more intuitive point of view. And then we'll start sort of we'll work a bit as well, so that in the next lecture we can talk about information geometry. Okay. So let's then start with the definition of likelihood. So this is definition 3 now. So definition 3, so let's start then with the statistical model as usual. So let this be, so as I just said, a statistical model, which I will write as SM for the P, so for the distribution or for the law of our friend capital X, the random variable, and then let also x1 to xn, and these are clearly lowercase letters or lowercase x's, be realizations of a sample, and these are now capital X's of X. Okay, so I remind you that these are random variables that are IID, okay, copies, well, IID copies of the capital X. Okay, so we can now define the likelihood function. And this we can say of the model, of the statistical model, is defined as follows. So we have ln, so we generally call it capital Ln, and this is, so by independence, and this is the same calculation that we did at the end of the last lecture, so by independence and by the identical distributions, right? We have that this is the joint distribution of the sample. Okay, so the likelihood function, the only difference with the joint distribution is that the joint distribution, generally speaking, it fixes the parameter, and then it's really just the arguments are really the values of the realizations. While what we're going to do now is to fix the value of the realizations, or at least have the random variables there, but actually ignore that bit and view this as a function of the parameter. Okay, and then under that, under such interpretation, then this is what is called the likelihood function. Okay, and this of course is defined for the parameter space. Yeah? So it's a function on that space. Okay, so we can also define the log likelihood function. Log likelihood function, and its normalized version. Sorry, that's not very well written. So it's normalized version. So these are defined as follows. Yeah? So we have, so we call them small n, small l. So this is going to be the log likelihood. So this is just simply this here. Again, this is going to be a function on the whole parameter space. And we also define this normalized version, which is no more than 1 over this ln theta. So if we, if we wish to write this explicitly in terms of the realizations, then this is going to be the log of the PMF or PDF at each of the realizations, and then at the theta as well. Okay, so this is a function of theta. Okay, just to clarify. Okay, so by the way, so we take the convention that log of 0 is minus infinity. Okay, all throughout, sort of silently. Okay, so maybe a few words about this, because the way I introduced it, the way I sort of introduced the logarithm in the last lecture was that we had this product that we saw up here, and if we wanted to do some calculations, so this was more like computationally friendly, then we wanted to take the logarithm, have a sum, and then we could derive an estimator from it. Yeah. So now what we have is that we've more generally written this likelihood function as or transformed it as some sort of sum, but actually it's a very special sum because the terms are going to be, so rather than having realizations, if we had the actual random variables, then these guys are going to be IID, and then we're taking the average of them. So then we should immediately be thinking already of, if we want to prove something about the likelihood function, then probably we want to go through the normalized version of the log likelihood and use some sort of law of large numbers, or even like a central limit theorem. Okay, so keep that in mind. We won't talk about it yet, but that's basically what will allow us, that's a key idea that will allow us to prove guarantees here. Okay, so now that we have this function, we can define now the maximum likelihood estimator properly. So definition, for, we have that a maximum likelihood estimator, which I will shorten as MLE, is any value theta hat. Okay, so this is an estimator that sometimes we will explicitly say that is the MLE, and this is a function of the sample, and it has to, of course, it has to belong to the parameter space, okay, for it to be a well-defined estimator. And what we want is that this guy is such that well, maximizes the log likelihood, right? So it's such that ln, maybe actually the maximum, so the maximum over the parameter space of the ln at theta, this, of course, the theta is running over the parameter space, equals the value at the estimator, right? Okay, so we can also equivalently define the MLE, of course, in terms of the log likelihood function. So same idea. We have that the max over the parameter space of the log likelihood should be equal to this guy, and we could even here put the normalized versions as well, of course, right? Okay, good. So now we've defined this. So let's make a few remarks about the MLE. So remarks maybe. The first one is that this estimator is a function only of the data, of the sample, And in fact, any randomness of this estimator will come precisely through the randomness of the sample, right? Okay. A second remark really is that we haven't really used to define the MLE and even to define the normalized version of the log likelihood, and therefore the log likelihood and the likelihood. We haven't really used the fact that we have a product and we have identically distributed random variables. I mean, we could just define things without any of that. Yeah? So what we can remark is that definitions 3 and 4, so they will make sense whenever we can. So whenever we have a joint distribution, really. Whenever whenever x1 to xn have a joint PMF or PDF, x1 to xn, depending on some theta, and so essentially what I'm saying here is that the IID-ness, if you like, is not needed. Okay. So maybe it's a good point to give a few examples. So I remind you that we already spoke about the Poisson statistical model, and another sort of prototype of model is the normal statistical model. So let's then okay. So if we have random variables, then that so let's say example. So then what we wish to consider now is x1 to xn that are IID according to a normal distribution with some mean mu and variance sigma squared. And I remind you that in this case, the theta is this pair, this vector, and let me maybe just write that properly, which will belong to this product space. Okay, good. Okay, so now so I'm going to skip some details here because this belongs to an example sheet really, and so in the example sheet, what you will have to do precisely is to find the maximum likelihood estimator of theta here. So you need to find actually two values. So just to help you out with the beginning, you should make sure that you understand why this is, and is that the log likelihood is going to be given by n/2 of the log of 2 pi minus n/2 of the log of sigma squared, and then minus 1/2 sigma squared, and the sum over the data points of xi minus mu squared. Okay, so after sort of convincing yourself that that is the right amount, I hope, the right quantity, then what you of course have to do is to set in the gradient of this guy to 0, right? Or setting this to 0, and then checking I guess negative definiteness of the Hessian of the log likelihood. This is from multivariate analysis. You should be arriving at the following, and is that the MLE in this model is going to be given by, of course, two MLEs, one for the mean and one for the variance, and these can be written. So I will define this quantity in a second, but these are given by these guys. Yeah? xi minus xn bar squared. Okay. So what is this xn bar? So xn bar is simply just the sample mean. 1/n of the sum of the samples. Okay. Right, good. So this is something you should check, and of course, what we have here is a very sort of intuitive solution, which is saying that that all if all the random variables have the same mean and variance, then we will estimate the mean by the sample mean and the variance by the sample variance. Okay, so after doing this example and doing the Poisson one, of which I spoke in detail last time, then so far the MLE is really doing something that makes a lot of sense, right? Okay, so let's now go into a second or a third maybe example, which is one that you will also cover in more detail in the example sheet in the first one, and this is the Gaussian linear model. Okay, so the Gaussian linear model that you, I think, must have seen in Stats 1b. So what is this model about? Well, what it tells us is that we have a vector of observations, capital Y, that is going to be, so this is, by the way, n times 1 dimensional. So this is going to be given by some matrix that, for simplicity, let's take it to be fixed, times some theta, which is a parameter in some parameter space, plus some epsilon, where the epsilon is normally distributed with zero mean and identity matrix. So it means that essentially what we have is a collection of independent standard normals, right? So this matrix that I was talking about is going to be n times p, and this guy is going to be p times 1. And so really what we're saying in the linear model is that, well, we have a vector here of so-called responses. So it's just a variable that we are interested in. And what we are really interested in, about this variable is how it changes as we, as some other variables change. Okay, so these other variables are precisely those that are essentially, that give rise to the matrix. And so these are called the covariates or the explanatory variables or the predictors. Depends on what field of stats you're coming from. And I guess, so we said that these are fixed. And so what the model is saying really is, okay, so I'm going to explain the y given the x's by a linear model, right? So for some theta that belongs to some parameter space that is contained in RP. And, it could be that the relationship is not perfect. And so rather, we're missing some covariates. So really, we haven't found every single, variable that could be explaining y. And so we have a bit of error here. And this we sort of assume, well, by the central limit theorem and, this kind of arguments, then maybe what we get is really a normal distribution. Yeah? So it could be also like a measurement error, or it's simply, as I was just explaining, our lack of understanding of the precise relationship between covariates and, the variable that we want to explain. For whatever reason, this is the Gaussian linear model, and this is this is at the absolute core of statistics, without a doubt, the most important model. So, but it has a peculiarity, at least for us, that we've been talking about samples as IID copies of a random variable. Well, actually, this doesn't really classify as an IID sample, because if we look at the ith observation, so one of the entries of this capital Y, so one element of the sample, then this is going to be given by the ith row of the X matrix times the theta plus epsilon I. Yeah. So we see, of course, that, you know, because the X's are not random and theta isn't random either, then because the epsilons are independent, then we get independence, but we don't really get identical distributions. Yeah? So not identically distributed. Let me just jump to the next line. Sorry, not identically distributed, but independent. Yeah? Independent only, and we do have, you know, and so we have the joint distribution. Yeah? So that's really what we wish to have, yeah? And to define a likelihood and MLE. Yeah? So, and this is so this is still, or this can still be specified. Yeah? So we can therefore, as I just said, define the likelihood and the likelihood, the maximum likelihood estimator. And in the example sheet, what you will see is that the MLE here actually coincides with the OLS estimator. So the OLS is the ordinary least squares estimator, and this is one that you must have seen in Stats 1B, and what we see again is that, you know, the MLE is a good estimator in this case. Yeah? In this case, in which actually we didn't even have the identical distribution. Now, why is it a good one? Well, I remind you, just because we'll sort of see related results later on in the course. I remind you that the OLS estimator is a good one, and actually is the best one in some sense. So by the Gauss-Markov theorem that you must have seen last year, is blue, right? What we shorten as blue. So that means the best linear unbiased estimator. So this means that the meaning of this theorem is saying, well, if you look at, or if you look for an estimator that is linear and unbiased in this model, in the Gaussian linear model, then the one that is the best in terms of least variance is the OLS. And so the MLE is also going to, of course, recover this property because it is equal, right, to the OLS. And so this will connect to information theory. Yeah? So having the minimum variance means that you're extracting as much information as there is from the sample. Yeah? So it's the best in that sense. Okay, so a third remark here that is due is the following, and it's just so that we complete the picture in some generality. So what we can say is that in other situations too, the MLE, so in other situations or settings or models, essentially, that's what we're saying, the MLE is the unique, so this is the unique maximum of the log likelihood, but it can also be the unique zero, of the so-called scorer function. And this we denote by capital SN theta, which is just the gradient with respect to the whole parameter of the log likelihood function. Okay, and so when we equate this score function to zero, that becomes the score equation, or the equations if you have you're in a multidimensional setting, which we generally will be. So by the way, in terms of, so what I'm saying here is that, so Sn at this theta hat is zero, and this is with the following notation. So the notation here is simply that Sn at theta prime means the gradient with respect to theta, and then evaluated at the theta prime, right? Okay, very well. So we are basically done with this. So what we have now described is essentially a general estimator that we can build as soon as we have a likelihood function, right? And so far, so good, right? What we've been seeing is that, well, it makes perfect sense in the Poisson model, in the normal model, and actually in the Gaussian linear model, which is not even IID, the observations are not even IID, then it turns out to be the best estimator, at least within unbiased and linear estimators. Okay, so let's now move on then to talk a bit more in a bit more detail about the likelihood function, and then talk about what is called information geometry, which is is a way of so we can get intuition for the MLE through information theory. Okay, so so then this is 2. So this is the likelihood function. So the and information geometry. Okay. So the likelihood function we've of course just defined. So let me just introduce a bit of notation. So we're going to, I know I said in the last, in the first lecture that we only, I didn't say only, I presume, but I said that we will focus on one-dimensional random variables, but actually we can develop this theory for more general random variables, even though, inherently we're looking at a one-dimensional quantity, or at least for this lecture. So we'll see this in a sec. So let X, just as usual, be distributed according to this distributional law, capital P, and we're going to allow it to take values in what is called the sample space that, as I just said, is not necessarily only on R or within R. It's not a subset of R only, but it can be a subset of RD for some D that is maybe larger than 1. Yeah? So the other thing we need is a function that is going to take us from this sample space to the real numbers, and then we're going to look at the composition of these two mappings and say something about this now one-dimensional random variable. So then let's see. So then if so if we have a statistical model, so if this is a correctly specified statistical model, I would write it as SM. And I'm sorry, I'm shortening a lot of things, but I hope that with the recordings it shouldn't it shouldn't bring up confusion. So you can always go back to it. So a statistical model for P. Then I wish to introduce some notation, and that is that, so I want to define E, so the expectation with some subscript theta, to be essentially just the expectation with respect to the P theta, Gx, or simply the expectation of Gx, right? So we have that. So this theta, by the way, maybe we can say like it would be a theta naught, if you like. So it's one that, the one that corresponds to the X, at least one, because we only said correctly specified. So we didn't say that we have an identifiable on top of that model. And this, just for clarity, can be written, in the case in which we have a discrete random variable, then this is simply the sum of the Gx's times the PMF evaluated at each of the x's of the sample space, and this at theta naught. And then in the continuous case, so this would be discrete. And in the continuous case, this is simply the integral over the sample space of this Gx, and then the F. So we have the density, the probability density function, right? And the X. And this is continuous case. Okay, so given this notation, we can now talk in more detail about the likelihood function. So let's make a couple of observations really. So let's start with the following. So I guess what we want to get intuition on is, not only through the examples that we showed, but also just more generally, we want to say that the MLE is really making sense in whatever way we want to say it. Yeah. And so let me go back to the beginning of the lecture, in which we were looking at this quantity that I was underlying, right, as the normalized log likelihood, because I said we could use some sort of law of large numbers. Now, what would be the assumption that we need to use some law of large numbers? Well, we need the expectation of each of these random variables and actually of the absolute values to be finite, right? So if we have that, then what we are going to get, so we have the following observation here. So if the statistical model that we have at hand is such that, so if it is such that the expectation of the absolute value of these logarithms is less than infinity, and this is for all the thetas in the sample space, if you like, let's just write it. Then what we get is that this guy's normalized log likelihood is the sample version or the sample approximation to or of this quantity. We're going to define as L theta, and this is going to be defined as simply just the expectation of a log, right? Okay, so so we now have a target in some sense, and we wish to understand this target, right? So now it wouldn't really make sense to try to understand this without having a parameter that is really, after all, what we're looking at, what we're going after is a parameter, right? That is giving rise to the unknown distribution, right? That is corresponding to the sample. So let's assume then that we have first of all correctly specified model. So if we have that, the statistical model is correctly specified, then the question would be, what thetas are going to maximize this L, right? Because maximize this L theta, which now we can write as, with the subscript of theta, maybe with some, okay, let's, yes, so theta naught here, yeah. So imagine that, so it could be that there are several theta naughts. So I haven't said identifiable model, I've simply said correctly specified. So this is a theta naught, by the way. Yeah. Doesn't look pretty good, but it's a theta naught. Okay, so which ones maximize this? Well, I mean, we would like precisely to have theta naught to maximize this, right? And that should be apparent to everyone, because if this guy is a sample approximation, with the MLE, we want it to be close to theta naught. So ideally, if this guy is an approximation to this, then maybe, the maximizer of this guy should be what the maximizer of this other guy is approximating. Yeah. So then we really, what we want is this theta naught to be the maximizer. So then now that we have that intuition, then let's look at the difference between L theta naught and L theta, and what we want to ideally show is that this is non-negative, right? So that theta naught is really the maximizer, and so we can write this simply as the negative expectation and the theta naught of the log of fx theta divided by fx theta naught, right? Okay, so now what we can use is Jensen's inequality here because we have a logarithm, so and actually with a minus, so recall Jensen's inequality, which says that if we have a function phi, so if phi is convex, then it's, or the image through it of the expectation of the function that we're looking at is going to be less or equal than the expectation of the image through this phi. Yeah? Okay, so this is the Jensen's inequality. So recall this, then. So then, what we can say is that these guys, so this guy that we can call maybe star. So we know that star is going to be, well, I guess, larger, greater than or equal to, so we are applying now this sort of reversed, is going to be the minus log of the expectation and the theta naught of this ratio that we had in there. Okay. Right? And I mean, this is a very, so what's going to happen here is that, you know, this expectation, if you go back to our definition of this expectation with the subscript, then we have that, you know, we have a product between the G and the F, and here also a product, the G and the F, and therefore these two guys, so the, you know, the F that is coming from here and this F here are going to cancel out. Yeah? And so what we're going to get is minus log of 1, which is of course 0. Yeah? And that's exactly what we wanted. So theta naught maximizes L, and we haven't really used a lot of assumptions here, right? We really haven't. We simply have that. So this, by the way, yes. So we simply have that. The model is correctly specified. That is it. And this is, by the way, so, okay, so maybe let's just go to the next page. So this means that, as I was just saying, this is a maximizer. Yeah. Furthermore, so we can say more. Further, if the statistical model is identifiable, okay, two, as in addition to the correctly specified case, then we can use the so by the strict monotonicity of the logarithm and strict Jensen's inequality, then what we have is even stronger, is that L theta naught, which is going to be now the unique parameter. Sorry, this should, is now going to be strictly larger than L theta, for all theta. So if we add identifiability in addition to correct specification of the model, then this is going to be the unique maximizer. And then, of course, this is for all theta that is not theta naught. Okay. Right. Okay. So I guess what this is telling us is then that if we had some sort of regularity assumption, right? So if this, so remember that the normalized log likelihood is a sample approximation to this L, then if it is a very good approximation, right, sort of like uniformly around the maximum, then and it is continuous in this kind of regularity assumptions, then we will get that the maximum is actually not far from the maximum of L, right? And so the MLE is going to be close to theta naught. Okay, so this is intuition so far, but we will use this in the proofs. We're just simply not ready yet to, technically we're not ready to prove anything about the MLE yet, but this is, the intuition, one of the bits of the intuition that we will be using. So, so just to emphasize this again, so then note that under some regularity or sufficiently, or this is like hope, under sufficient regularity assumptions, we're going to have precisely that. The maximizer of this guy is approximately that of this guy. Yeah? So this is, by the way, of course, the parameter that we're looking for. Okay. So let's make a remark here, yet another remark that, so that we connect this to information theory, because, so far what we've said is that, yes, okay, so this is a good reason to think that this is going to theta naught, but is there, but this is sort of like coming out of nowhere. So is there more intuition that is behind why the MLE could be a good estimate of theta naught? Well, yes, so we can do that through information theory. And so let me just make this remark. So the quantity that we're looking at, so this is this expectation that we were looking at. So this expectation and the theta naught of the log of fx theta naught divided by this guy, which is, I remind you, just simply the difference of these two guys. So this has a name and is generally called, so this is often referred to as the entropy, or also the, the entropy or the Kullback labeler divergence between the two PMFs or PDFs or actually distributions. So I will tell you something about it in a sec between this and this. So by the way, we are so far, in this course we will not worry too much about measure theory, and but what I want to say here is that this Kullback-Leibler divergence can be defined just for general distributions or probability distributions, and that you can do through Radon-Nikodym derivatives. But if you want to learn about that, then you should go to probability and measure. We're not going to need it, but just to make you aware of it. Okay. So something important about this is that it is a, let me maybe be a bit pedantic here, but this is a quasi and also semi distance. So it's not really a distance because it is not symmetric, and the triangle inequality doesn't hold actually either. And so this is some sort of distance, if you like, very sort of informally speaking, between precisely again between these two quantities, and actually more generally through measure theory, distance between distributions. And something nice about it is that it has a nice information or a fundamental information theory interpretation, which is as follows. So what we have is that this KL divergence is the information loss of approximating f theta naught by f theta. Okay. So what does that mean then in terms of the MLE? So if we think about this normalized log likelihood as simply an approximation to this ln, and we look at the difference between these two guys, then really what this is saying, and okay, so the approximation, by the way, would be for both L's, but this would be in some sense like the approximation to the normalized log likelihood evaluated at the MLE, for instance, because we were arguing that the MLE will be close to theta naught under some regularity assumptions. So then what we get really is that the value that will minimize the information loss is indeed the MLE, or the theta naught, in this non-approximate version. That's obvious, of course, theta naught should be the best. But the MLE is more important because the MLE is what we can construct from the data. And so what this is saying essentially is that the MLE, or at least the approximation that we would get, will minimize the loss of information from the data. And this connects very nicely with the Gauss-Markov theorem that we were speaking about before, in which it says that the OLS, or in this case the MLE, will have the least variance, which means that it will extract as much information as possible from the sample. And you'll then be wondering, okay, so is there a generalization of this that applies to the MLE? And yes, there is something that we will see later on in the course, which is called the asymptotic efficiency of the MLE, and this means that the MLE will be, as you get more and more data, it will be efficient, and being efficient, informally would mean that you extract as much information as possible from the sample in a more, in a formal way or in a technical way. It means that you attain basically the best variance, minimal variance one can attain, and this bound, right, lower bound for the variance is what is called the Kramer-Rao bound that we will see in 1 to 2 lectures. Okay. So it is optimal in that sense, at least. Yeah. Okay, good. So let's now make a second observation. So observation 2. So second observation. So I guess so far, really, I mean, the way we were computing the MLE was through derivatives, right? And that was useful because we took the logarithm, you take the derivative, and actually the derivative of the logarithm generally works out very nicely. But I mean, that's only in toy problems. If we were to look at really more, problems that whose statistical model is a lot more complex, then actually maybe we cannot compute that derivative. We need to use numerical methods, but we're not really concerned with that in this course. Anyway, what I want to say is that at least when we're trying to compute things, we wish to take derivatives, right? So far, we've been getting intuition for the MLE, simply looking at the normalized log likelihood, but we haven't really said anything about the score function, right? And so that's something that we can do now, also because it is going to help us with the Kramer-Rao lower bound, basically. So it would be useful for two things. And so now what we wish to say is, well, remember the score function that is here. So this is going to be the gradient. So now if we want to apply, so remember, I mean, we have that this ln is simply some average, right? So it's this quantity here. So if we take the gradient of this, then is of course the 1 over n sum of the gradient of the logarithm, and we can then think again of a law of large numbers. And so what we need is the expectation of the absolute value of the gradient to be finite. Of course, that doesn't make sense because the gradient is a vector. So rather than the absolute value, what we take is the norm, and in fact, as you should be familiar, as you should come naturally to you, when we have norms of vectors, it's a lot easier to work with the squares of them. Yeah? So then really what I want to say here is that if the statistical model is such that we have that the norm of the gradient, the logarithm of this guy is, well, the square of it is finite, and this is again for all theta in here, then Sn, so just similarly to before, what we say is that Sn is the sample approximation to the expectation of the gradient, right, of the log. Well, maybe let's say the L from before. Okay, so that's fine. And now, okay, so let's recall, by the way, of course, that, so recall simply that the MLE satisfies the score equation, right? So, just I guess similarly to before, if we have that, so if the statistical model is correctly specified, for some theta naught, then I guess we can wonder whether this will now be 0, right? We could wonder about that. Yeah? Okay, so let me just not be so sloppy. So we can just write it here and say, well, it really is the expectation and the theta naught of this gradient, and the gradient evaluated at the theta naught, is this going to be 0, right? So this is analogous to the previous observation that we were talking about, right? So if it is, then that's good news again, right? Because what we're saying is that the target of this law of large numbers is actually 0 at the true value, and that's again that's good, yeah? Because the MLE is just the 0 of the sample version of this. Okay, so let's do some calculations to check this. To check if this is true, so let's assume that, so if theta is in the interior of the parameter space, then we can do the following. So we can do the following calculation, which is that the expectation under theta of the gradient of L theta, well, the gradient itself, thanks to the theta being in the interior, is going to be given by just simply the gradient of the PMF or PDF theta, and then divided by this PMF or PDF, right? And now maybe let me just do this for continuous random variables, but this is exactly the same idea for discrete random variables. But this, what we see again is that, just before, the PDF coming from integrating this with respect to that and this guy will cancel out, and so what we get here is just the integral over the sample space of the gradient of this guy, right? And okay, and we pause here for a second. So if we were physicists, then, and I apologize if there is anyone in the audience, but if we were, then we would probably take this gradient out easily of the integral, and then continue with that. Now that is not always true, of course, that you can do that, but so let's assume that we can. So for those cases in which we can, so if the statistical model is such that this gradient interchanges with the integral, then what we have is that the right-hand side is going to be equal to the gradient of this integral, which is of course 1, the integral I mean, and so again we get a 0. The 0 vector in this case. So we just sort of checked this, which is then telling us again that under some regularity assumptions, right? Because after all, this interchange of the derivative and integral is just assuming some underlying regularity. So under this regularity assumption in particular, what we have, well, and also very important, and if theta naught is in the interior of the parameter space, then what we have, well, we have that this guy, so this is going to be the L at theta naught, is centered, right? So that means that it has mean 0. It's centered under, of course, the true p theta naught, and furthermore, if we have this double star, which is going to be this guy here, okay. So if we have that, which we haven't used, so we used it for to motivate this through this law of large numbers, and so that's the conclusion I want to make. So if this is true, then we get that this guy is also centered. Yeah? Okay. And so this, well, this goes back to the comments that I was making at the beginning, but in addition to sort of telling us yet again that regularity assumptions will allow us to, to say things about the MLE somehow, it will also be useful to this calculation only under the assumption of being in the interior, and this interchange of the gradient and the integral will basically allow us to talk a bit more about information theory and eventually prove the Cramer-Rao low bound. So I hope you enjoyed this lecture, and I will see you again in lecture 3. Thank you for your attention.